So if we continue on here with our discussion about 3D connections and 3D reactions, I've got a 3D printed example of a ball and socket joint here. So see how I can rotate it about this axis. I can also rotate it here. I can rotate it here. So this is allowed to rotate in all three directions, but I can't move it. This is trapped in there. So historically, I just say, oh well, think about your shoulder, or your hip, how you can move your arm or your leg, and all you can rotate it about your joint in all different directions, and that kind of works. I don't know. I'm going to draw kind of maybe a simplified version of this here. I a lot of times goodness, it's been a while since I've tried to draw one. Maybe draw kind of a ball with maybe something coming out. I'll probably just draw it, and this is coming out in the Z direction. And like I said, I didn't promise a good drawing. Right? And so some kind of something or other holding it. Right? So I don't know, something like this maybe. So it doesn't really matter what direction you put X, Y, and Z, honestly. The hope is you can kind of see if this is point A at the origin, then what you have a reaction force in all three directions, because it can't come out. The ball cannot come out of the socket without breaking it or damaging it. I mean, you can dislocate a hip, or you can dislocate your shoulder. Any of you have done that before. It never goes back in quite the same. Takes years for that to kind of heal up to where it doesn't pop out again under stress. It'd be the same thing with this guy. If I had actually put enough force to pull this out, I would probably break these little tabs off, because those are 3D printed, and it's an older print. I've had this for a little while, probably 10 years I've had this. But you can see, right? If I put this where it's kind of like what I've got drawn here, if I try to pull this out in the Z direction, it won't come out. So there's a reaction force in the Z. If I try to push it in this X direction here, it won't move in the X direction either back or forth. So I've got a reaction force in the X direction being applied, and the same thing in the Y. If I try to push this thing in this Y direction, push or pull it either direction, I get a reaction force in the Y. But because it can rotate about the Y, it can rotate about the X, and it can rotate about that Z axis, there's no reaction moments. As opposed to the pen, which only is allowed, again, remember the pen, the hinge, is only allowed to rotate in one axis, but not the other two. So there's two reaction moments. There's only one free rotation for a pen, the direction of the pen. So if it's in the Y, we draw it like this. We talked about rotating that. But the ball and socket joint, though, allows complete rotation in all directions. But it doesn't allow movement in any of them, I should say. Okay, hopefully that helps. I always feel like that's a little... I loved my statics professor, but I feel like that's hopefully a little better. Actually seeing some of these in flesh maybe helps. There are some other types of reactions. Be sure you've looked at your table in your text. So when you encounter a reaction, some kind of connection that you're not used to seeing, go refer to that table in your text and say, oh, well, for a bearing, journal bearing, or a thrust bearing, what kind of reaction forces should that apply? And you're going to find in those problems throughout the book, again, I'm only assigning you the bare minimum homework problems. You should be practicing working a few more problems than what I've assigned. And when you encounter a connection you're not used to, go look at the table and see, okay, well, for this kind of connection, these are the reactions I need to apply at this point. And for this kind of reaction, these are it's just the one force. And for this kind of reaction, it's these forces in these moments. Right? And be kind of comfortable applying those. And if you're ever not sure about one, send me your free body diagram. And that is so easy for me to say, oh, no, you missed this. You missed a reaction force in this direction. Be sure and add that, and you should be able to set your equations up and be just fine. Okay? Okay. All right, what have I got next? I've got a couple of examples here. Okay. A couple of examples. Where am I putting this? Okay. Sorry, I'm in a new space. I'm trying to figure out where I put stuff when I'm done with it. I'm just going to start a new sheet of paper. This will be L10, page 3 of something. Don't know what it is yet. Example problem. Let's just keep this one. I think fixed supports are kind of some of the simplest ones, especially in 3D to work with. Just enough challenge. I'm going to draw the X kind of out here in a dotted line because I'm going to have a bar of some kind. I'm going to have this bar, this L-shaped bar. It's going to go 5 meters out in this positive X direction, and then it's going to curve and come a little bit shorter, 3 meters over here in the positive Y direction. And so draw that out, flesh that out into 3 dimensions here. So something like that. And again, I'm trying to keep most of my lines parallel to either X, Y, or Z direction. Excuse me. And this is my X, this is my Y, this is my Z. And however you want to make this appear to be some sort of a fixed support, this is a fixed support here at the origin, or we're just going to call it point A. I like to call things point A a lot. You guys haven't already figured that out. Point A. And it's going to be find the reactions at A, which is, again, it's a fixed support. So find the reactions at A. And the other thing we need to know is, all right, well, what's applied to this thing? Well, there's going to be a couple of forces applied here. So there's going to be this force that's applied in the XY direction, so it's negative X, negative Y. So there's a force out here at the end being applied in the XY plane. So this force here is being applied, very poorly drawn, like this. It's going to be minus 9 in the I direction, minus 12 in the J direction. That's going to be newtons. And there's going to be a force right here at the very tip of the x-axis, right where it turns back to go in the y-axis there. There's a force straight down here of minus 30 k newtons. So straight down force. This looks like it's a straight up force. This is not an up force. This is in the xy plane. It's kind of hard to show that in three on a 2D media. Try to draw a three-dimensional force. That's the reason. Part of the reason why, when you give me a magnitude of a force, that's not the complete picture. I need to know, either what is the direction associated with that magnitude, or the simplest thing is just give me the components. Anyway, we want to know what are the reactions at point A of this fixed support. You also need to know the lengths of this thing. So this thing comes out 3 meters in the positive y direction and 5 meters in the positive x direction. And this bar is just out here in the xy plane. No z, there's no elevation change for this bar here. Okay, all right. What do we do here? Well, if you go to your table in your text, it talks about what do you expect at a fixed support. So a fixed support doesn't allow movement and it doesn't allow rotation. So that means that this fixed support is going to apply a reaction force and a reaction moment in all three directions. So if I draw my free body diagram of this arm here, so I don't have to draw quite as much detail here. I can just draw kind of this wireframe. A little bit longer in the X than it is in the Y. I'm going to dot my Y direction, dot my Z direction, extend out just a little bit further my X direction there. Again, I've got a force straight down. I'm just going to say 30. 30K. It's not kilonewtons, by the way. I was like, wait. It's not kilonewtons. That's 30 in the K direction newtons. So it's 30 newtons straight down. Okay. And then out here at the end of this bar, in the negative X direction, so I'm going to draw this in the negative X direction. I'm going to break this force I've got here into its components. I just very much prefer to draw forces and their components on a free body diagram. So in the X direction, I've got 9 newtons pointed in the negative X direction. And then I've got 12 newtons pointed in the negative Y direction. This is the positive Y, so back this way is the negative Y direction. And then you can kind of darken this in a bit so you can see it a little bit better. And again, distances here. 5 meters along the positive x-axis, 3 meters out there in the positive y-axis. Okay, and then what else we got? We've got a fixed support here at point A. So that fixed support means that I have a reaction force, AX. I've got a reaction force, AY. Now fixed supports, they get kind of busy because you've got 6 unknowns you've got to label all at one point. So I've got a force in all 3 directions, AX, AY, AZ, force in all 3 directions. I also have a reaction moment because this thing is basically it's like concreted in there. It is not allowed to rotate in the Y, it's not allowed to rotate in the Z, it's not allowed to rotate in the X. This thing is fixed in there. It will not move, and it won't rotate. So I've got forces to keep it from moving, but I also need to apply rotational or moments, reaction moment in the X, reaction moment in the Z, and reaction moment in the Y. So I've got all 3 of those. I've got reaction moments in all 3 directions and reaction forces in all 3 directions. Notice the way I've drawn those. I'm following right-hand rule, right? So if I point my thumb in the positive Z direction, it goes like this. So that means this is rotating like this. And if I put my thumb in the positive X direction, the direction my fingers close shows me the rotation for positive X. So that means going around like this. And I can't quite do it here. Positive Y direction, fingers close like this. So that means rotation is like this. The direction your fingers close shows you the positive direction of rotation about that axis. Okay. Now, how do we do this? Now, there's a couple things you could do. Let's do forces first. Those are easy. The forces are real simple here, looks like. Again, our steps, normal procedure here. What are we looking for? Reactions at point A. I have 6 of them. So I have 6 unknowns I'm looking for here. Next step, what do? Well, I draw a free body diagram that shows those. Then I apply equilibrium. So let's write equilibrium equations. Let's do our force equations. Those are simple. Sum of forces in the x direction, 0. I've got minus 9 newtons here, and I've got plus AX. That's easy enough. Sum of forces in the y direction, equal to 0. I've got minus 12 newtons there, plus AY. And that's it. You could write AY minus 12 newtons, same difference, tomato, tomato. Sum of forces in the z direction, equal to 0. We can write AZ first if you like. You can write the minus 30 newtons first, whichever you like. I've got 30 newtons going down, I've got AZ going up. So it's AZ minus 30 newtons or minus 30 newtons plus AZ, whichever way you want to write it. 3 equations, 3 unknowns so far. But again, I've got 6 unknowns here. I've got these unknown reaction moments I need to find. How do I find those? Reaction, or I apply equilibrium to the moments. Now, you can do this a couple of ways. We talked about when we find reaction summation of moment vectors, what you can do is you can add up all of the R cross F. So you've got different forces, right? Remember back here, you've got one force here and you got another force there. So you could do the moment caused by this force. So find a find the line of action for this force, find a position vector to go from this point to the line of action of this force, and that serves as your r cross f for this first force. And you could do the same thing. I can write a position vector from here to the line of action of this force. That serves as my r, and then cross that with this this vector here. And so I've got two forces, so I would need to do two cross products, add up those moments, and then set those equal to then, I've got, that's not true. I've got sum of all the r cross f's, and then add to it then m rx in the I direction, add to it m ry in the j direction, and add to it m rz in the k direction. All right. So this is all one equation. Add up r cross with all the forces, and add to it any couple moments that are on your free body diagram. I've got 3 couple moments on my free body diagram. Add those in. And you can do that. There's nothing wrong with that. I might work that out on a separate sheet of paper and just show it to you later. But that's not how I'm going to solve these. I cheat a little bit. I say it's cheating. I think it's a perfectly valid way to find these. I just find, let's just look at all the moments in the x direction or about the x-axis, because those are all going to add up to be 0. So if I look at the moments caused about the x-axis, that's a good stopping place. We're going to pause there, and we're going to pick up the next video. I'm going to show you how do I find the moments in all 3 of these directions, moments in the x, y, and z. And that's where we're going to pick up the next video.